The sun at the centre of our solar system surrounds us every single day, from the day we were born until the day that we die. Even on days filled with cloud coverage and rain showers, the sun's rays still shine through somewhere on Earth, and at night its radiance reflects off the moon to keep us lit, even during darkness. It's easy to think of the sun as an eternal object, one without creation or demise, an infinite source of hope and happiness. Unfortunately, our sun is anything but eternal or infinite. It had a beginning, and it most certainly will have an end. While we won't be around long enough to witness our world without the sun, it's an intriguing process to dive deeper into the timeline of our solar system's nucleus. Using information we already have about its birth and modern-day existence, we can dissect the models and come to a conclusion for what happens when the sun ultimately dies and our corner of the galaxy officially goes dark for good. About 8.5 billion years after the universe was born, or just 4.5 billion years ago from today, there existed a massive molecular cloud made up of mostly hydrogen and helium around the area of our modern-day solar system. In the middle of the hydrogen and helium was a source of gravity, strengthening by the second. Combined with the trapped pressure between gaseous molecules, the gravity increased the heat within the totality of the cloud. To figure out exactly how the molecular cloud originated, astronomers turned to ancient meteorites in hopes to paint a better portrait of how old our universe truly is. Some of the space material they tested radiometric dates on was estimated to be 4.567 billion years old, the oldest object of our solar system to be collected. These ancient space rocks contain stable daughter nuclei of short-lived isotopes, radioactive particles of an element that can only be created in explosive stars that don't live very long either. One such short-lived isotope is iron-60, found on the exact ancient meteorites these astronomers were testing. Because the findings from the meteorites aligned with the computer models researchers had been using whilst charting stellar evolution, it was safe to say they originated from the event that created the starburst 4.6 billion years ago. Not only that, but astronomers for the first time confirmed their belief that the molecular cloud of hydrogen and helium was most likely impacted by one or more supernovae events in the general vicinity. These supernovae would have produced shockwaves that eventually compressed all of the matter trapped within the molecular cloud. Eventually, that giant molecular cloud started to implode bit by bit and collapse in on itself. One section of the cloud would fall, followed by another. As a result, the internal mass of the cloud began to get squeezed towards the center, like a bottle of toothpaste at the end of its life. In addition, the cloud itself started rotating at a constant rate due to the conservation of angular momentum. With rotation came the increase of heat and energy. The heat and energy then coalesced to the center, where the burgeoning mass was forced. Once the generated heat increased at the center, the entire molecular cloud erupted. The center remained a concrete sphere of mass. However, other matter within the cloud flattened into a disk of rock and gas, forming the prehistoric exoskeleton of our modern-day planets and the other assorted objects in the solar system. The centered mass in the middle of the disk wasn't done absorbing energy, however. As the disk first materialized, the core eventually collected additional matter from the fragments of the disk's genesis. With the ever-increasing gravity and pressure at the center, the core's matter accumulation caused what is known as nuclear fusion. Nuclear fusion, also called stellar nucleosynthesis, is the birth of a star through reactions of chemical elements, including popular ones such as hydrogen, helium, and lithium. These reactions have been commonly detected all across the universe, dating back to the Big Bang. The composition eventually changes due to an overabundance of chemical elements, and starts burning bright enough to form a star. This is exactly what happened to the once molecular cloud turned hot ball of plasma, better known as the Sun, our home star. In the billions of years since our Sun's formation, it has since evolved into a yellow dwarf star, also known as a G-type main sequence star. On average, yellow dwarfs burn between 5,300 and 6,000 Kelvin and fuse around 600 million tons of hydrogen and helium together per second. This is the equivalent to converting 4 million tons of matter into energy every second, making yellow dwarf stars and the Sun itself true celestial workhorses. It is also the equivalent of converting 100 times the mass of Earth into energy, which is still only 0.03% the mass of the Sun. So while the Sun produces an incredibly immense amount of energy, it won't even reach 0.1% of the Sun's total mass at the end of its life cycle. Regardless, with each tick of the clock, the Sun creates solar radiation and neutral subatomic particles called neutrinos. Solar radiation, or solar irradiance, is what directly engages with the physiology of plants, the behavior of animals, and newer energy sourcing technologies, such as solar power plants. In terms of our specific yellow dwarf, it finds itself halfway through its current stage of being a star, also known as its main sequence stage. It has about 5.4 billion more years to go, fusing hydrogen and helium for a total of 10 billion years. Like all stars, the Sun gradually increases in temperature at its center and on the surface, while the radius also increases inside. The Sun also very slowly increases in luminosity, becoming brighter as the main sequence lingers on. For perspective, since the yellow dwarf came to be and started its nuclear fusion, its radius has grown by 15%. The surface temperature, which was once 5,620 Kelvin, has heated up to nearly 5,777 Kelvin. The Sun also used to be only half as bright, jumping from 0.677 solar luminosities to a 1.0 solar luminosity reading. The increase in brightness is due mainly to a decrease in thermal pressure, as helium atoms within the yellow dwarf's core come with a higher mean molecular weight than hydrogen atoms as they were fused together. It also stems from the release of gravitational potential energy by the Sun, of which 50% is converted to heat as brightness increases. In layman's terms, this also means the Sun's core is gradually shrinking, as the outer layers move in towards the middle of the sphere, resembling the activity of the giant molecular cloud of which the Sun originated from. And as the Sun's outer sheaths collapse towards the center, the core becomes denser and denser, speeding up the process of the Sun's fusion. At the rate it's currently burning, the Sun will increase in brightness by a rate of 1% in solar luminosities every 100 million years. At 1.1 solar luminosities, the Sun will be bright enough to deplete all the liquid water molecules on Earth, scheduled to occur in around 1 billion years and 3.5 billion years from its slow death. The next and final phases of the Sun are quite explosive, yet not on the level of a supernovae. Our local yellow dwarf doesn't have quite enough mass to create such a violent celestial event, but its demise will be nothing short of spectacular. Rather, the Sun is set to run out of hydrogen in about 5 billion years. The contraction of the core will cease, but the luminosity will only grow, forcing the star to exit the main sequence stage and expand into a subgiant star, followed by a red giant. The luminosity itself will reach a point 1,000 times brighter than the Sun currently shines. Once the Sun reaches its red giant phase, it will be big enough to swallow both Mercury and Venus, with some estimates charting the red giant Sun to completely engulf Earth as well. And if the Earth is still around, and by some models it will be due to a wider orbit caused by the Sun's loss of mass, tidal forces will cause the Earth to shrink its orbit anyway, sending the Earth into the tip of the red giant's crown. This phase will last about 1 billion years, before the red giant branch phasing forces the star to lose a third of its mass. From the red giant branch, the Sun enters the first of the final phases that will encompass another 120 million years. The core will initially ignite due to a helium flash and convert to carbon, drastically changing 40% of the Sun's mass. Not long after, the dying star will decrease in size tenfold, in luminosity by 50, and the temperature will actually retract to modern-day temps. As these decreases continue, the Sun becomes a horizontal branch and once again grows in all aspects of the star as the helium reignites and the process starts over. After 100 million years from here, the helium source will be all but exhausted, and the Sun will do what it did when it first ran out of hydrogen, expanding in size and brightness by large margins. This is called the asymptotic giant branch phase. It will last another 20 million years before the Sun finally becomes totally unstable. From here on out, every 100,000 years, what's left of the star will undergo a very fast loss of mass, followed by thermal pulses that last a couple hundred years. As these thermal pulse patterns repeat, they also grow in strength due to gravity. These will cause the luminosity to reach heights of 5,000 times the modern-day brightness. After 5 thermal pulse cycles, the Sun will lose all of its exterior envelope and will become a planetary nebula at a mass of half of what the yellow dwarf currently withholds. The leftover planetary nebula will then only last about 10,000 years, shredding itself as a blue loop and leaving the core nothing but a naked white dwarf star, the final phase in a star's life. The remaining white dwarf will actually last trillions of years, and could eventually become a theoretical black dwarf, a star without enough heat or light to burn. However, the lifespan of white dwarfs is estimated to last longer than the current age of the universe, meaning one hasn't been observed to this point. So what does this mean for the rest of the solar system? While the envelope that the star sheds once it reaches its planetary nebula stage will be jettisoned into space in the form of gas and dust, but the other planets in our solar system may not be around to witness that. Mercury and Venus will be swallowed by the red giant, as well as Earth depending on the model you are using. The other planets will most likely be pulled and pushed into varying orbits, different from what occurs in present-day astronomy, due to the vast changes in gravity of the Sun's elongated demise. Depending on how destabilized the planets become, they could be pushed out of the solar system entirely, becoming rogue planets left to wander the Milky Way. Luckily, nothing even remotely close to these processes is expected to occur in the next few billion years, and with how the world is turning these days, we will probably be long gone before we have to witness such volatile destruction across our little corner of the cosmos.